Rollins from the University of Tennessee at Chattanooga in the United States. It's my first time in Dubai. Thank you so much for number one, having such a great conference for everybody to attend. Number two, coming to this talk. Thank you for being willing to spend some time learning about a new technology. I'd like to spend just a couple of minutes talking about innovation and how innovation can change our lives. Just 46 years ago, the United States put a man on the moon, 1969. I was talking with a friend earlier who has a great interest in the U.S. space program, and I know very little about the U.S. space program other than what I've seen on television. But he was explaining to me that at the time, in 1969, there was so little data storage, digital data storage, that they couldn't take a big computer up on the rocket ships to go to the moon. So they would have to actually transmit data in real time going to the rocket ship with navigation information to get to the moon. That seems amazing to us. We have more computing power today in our telephones than they had on the rocket ships that went to the moon in 1969. Innovation is something that happens when we have to meet a need or a strong desire. The American Society of Civil Engineers recently put out a report that told us that 1 in 6 bridges in the United States is in need of replacement. 1 in 6. There are many thousands of bridges in the United States. We don't have the money at the moment to replace 1 in 6 bridges in the U.S. And this got me to thinking, we have to change the way that we address our civil infrastructure, whether it's bridges or whether it's ports or whether it's roadways that are concrete or asphalt. And there are 2 real ways that we can affect sustainability. Number one, we can begin using recycled materials more and more so that the sources of the raw materials are renewable. Or number 2, we can begin to design concrete structures to last longer than they do. Concrete structures at present, in the US anyway, concrete structures at present don't last nearly as long as they should or could if they were designed properly with durable concrete. I got the opportunity to begin researching colloidal nanosilicas about 4 years ago when a Chattanooga-based company asked me if I could spend some time with it. And the things that they were telling me that they thought their material could do sounded unbelievable at first. I'm a research guy, I'm skeptical. But at the same time, I knew that the only way to test for innovation and test new things is to give it some time in the laboratory, see if it works, and then go to the field, see if it works in the field. So I want to take you through a little bit of that journey today. At the time, 4 years ago, when I did a literature review to see if there was anything out there on colloidal nanosilica, there was very, very little. But now, there's several papers, probably 50 papers or so, maybe a little more, from researchers all over the world that have studied this topic. So it's something that is gaining some attention. Just as an introduction, to tell you what colloidal nanosilica is it's very, very small particles of silicon dioxide. It's an amorphous silicon dioxide, typically somewhere between 1 and 500 nanometers. They're small enough where they can remain suspended in a solution, suspended in water, and the forces of gravity actually don't cause them to fall out of that suspension. So they're very, very small. But it's not a solution. It's not like a silicate solution, which is going to be where the silicon dioxide is coupled with some metal ion of some kind. The colloidal silica the particles can actually be seen under heavy magnification. And you can see that they're spherical in nature. But they're sufficiently large enough to show differences from true solutions. The way they work in general, this is just a brief overview, is that they react in a way that is very similar to the traditional pozzolanic reaction, which many of you, if you've studied concrete, know what that is. It's where a silicon-bearing material reacts with existing calcium hydroxide to form more calcium silicate hydrate. Calcium silicate hydrate is one of the 4 main reaction products of the cement and water hydration reaction. So this secondary formation of calcium silicate hydrate can happen later. These pozzolanic additives make up things that you've probably heard of, like fly ash, silica fume, ground granulated blast furnace slag, or GGBFS slag cements. Those things all have pozzolanic reactions that are very similar to what we're going to be talking about today, the colloidal nanosilica. And we see that from the literature, we see that the colloidal silica is an excellent source of pozzolanic reactions, mainly because it doesn't really differ all that much chemically from the other pozzolans that I just mentioned, but its very, very small particle size makes it highly reactive. So it's able to really undergo some serious reactions due to the very small particle size, which we know that very small particle size equals much more surface area, etc. So we know that when concrete is first placed, it's at its greatest volume most of the time. So you have water of convenience that's there above the water that's needed for the chemical reaction hydration to take place. That water leaves, the evaporable water leaves the concrete, forming capillary voids, or capillary voids, as my Australian friends like to say. Those capillary voids are like little rivers that form as the water evaporates from the concrete. The problem is that those capillary voids can, not only are they the way that water leaves, but they're also the way that water and other contaminants can enter the concrete. We know that permeability to water has been linked to durability of concrete. It's the primary indicator of how long concrete is going to last, especially in the case of reinforced concrete. Well, when colloidal nanosilica is applied, I'm specifically speaking today about post-applied colloidal nanosilica. There's been a lot of research done on integral colloidal nanosilica that's mixed with the concrete. What I'm talking about today is a post-applied, meaning the concrete's mixed, the concrete sets, gains initial set, and then the colloidal nanosilica is added as a spray. And it can be added at various times in the life cycle. It can be added from just as initial set occurs, or it can be added many months or years later. And similar effects have been noticed. Similar positive effects have been noticed from the colloidal nanosilica addition. So in post-treated CNS, I'm going to start referring to colloidal nanosilica as CNS, okay? Because it's a lot to say. In post-treated CNS applications, the pore space filled is generally going to be that capillary pore space that I was talking about, the capillary voids that come when the water of convenience leaves the system. So as that capillary void space is filled, it's easy to imagine that a lot of the hardened properties of concrete can then be improved. So the primary filling mechanism from the literature review, the primary filling mechanism is that pozzolanic reaction we were talking about. It's taking calcium hydroxide, reacting with it and forming more calcium silicate hydrate, which begins to fill that capillary void space. So if you think about it carefully, if you reduce the amount of void space in the concrete, then there are a lot of hardened properties that are likely to improve. We're going to take a look at those. We're going to see the effects on compressive strengths, effects on drying shrinkage, effects on permeability. We're going to take a look at corrosion modeling based on reduced permeability. And we're going to look at a case study that we did in the port of Marseille, France, on a boat dock there. The port wanted to try colloidal silica because they had tried many other things to increase the durability of their concrete, and they approached us and asked if we could assist in this case study. So I want to share some compressive strength effects. These are from researchers, not me. These are previous researchers in the field. And not all of these are post-applied. Some of them are colloidal silica effect in the convention, as an integral admixture into the concrete. But the effects are the same. And you can see this great lot of researchers have all demonstrated increased compressive strength. There's some thrown in there: increased flexural strength, increased bonding strength, etc. This is just continuing. So the researchers that have shown those strength improvements by using colloidal nanosilica. These are from the laboratory, the University of Tennessee Chattanooga laboratory, as well as some other laboratories. My work was here from 2012 to 2014. 2009, I think, was mostly done at Middle Tennessee State University, and it was not me. I think Dr. Heather Brown did that work. And 2000 was done somewhere else as well. I'm not exactly sure there. But you can see that compressive strength increases with the use of a spray applied colloidal nanosilica, ranging from 11% to 24, 25%. That seems like a big range between the amount of improvement that you're getting, but you have to consider these are not all the same concrete mixes. The concrete mixes are various permeability, various porosity, various water to cement ratios. So one key thing to understand about a spray applied colloidal silica is that the effectiveness or the amount of compressive strength gain that you might get is related to how permeable the concrete is to begin with. So we know that concrete varies with permeability. The primary driver of that is going to be water to cement ratio, but other things can also affect it, such as aggregate gradation or particle size, aggregate shape. There are many, even the mix of cementitious materials such as cement, fly ash, how those particles fit together and pack together. So all of those things can affect permeability, but typically water to cement ratio is looked at as one of the primary indicators of where your permeability is going to be. Here we see from 2015 the compressive strength effects from the laboratory, post-applied CNS. And it's kind of hard to read, but you can see that down here, this is a kind of a curing study where we broke several samples at various ages. And you can see that we have the control being here, and this is various applications of colloidal nanosilica. I want to switch to effects on drying shrinkage, and you may be saying to yourself, wait a minute. Okay, so it affects compressive strength. We get an increase in compressive strength, and now you're going to tell us that it also does something with drying shrinkage. Well, yeah, because remember, the primary way, or the only effect, the only really effect that the colloidal nanosilica is having is it's filling pore space. And filling pore space, a lot of good things happen when you close that pore space. So drying shrinkage, we know from the academic literature that colloidal nanosilica reduces drying shrinkage by quite a bit. And these are, this is a graph from a researcher named Duke in 2015. And you can see he has various percentages. These are percentages of colloidal nanosilica. This was actually not a spray applied test. This was done as an integral admixture. But you can see the control is here, ordinary Portland cement at the top, and you can see the drying shrinkage and microstrain decreasing. It looks like the optimum percentage that he found was around 1.5% colloidal nanosilica. Effects on drying shrinkage from my laboratory and others show a range. 2012 to 2013 is when we did this testing. From 46% to 61% or so. This is the post-applied colloidal nanosilica. And this again is not just UTC laboratory. There were a few of these studies that were done at Middle Tennessee State concurrently. And you can see that the drying shrinkage, this was a really high water to cement ratio here for the control. And you can see this is, again, there was an improvement there, but it was a very high water cement ratio mix. So that's a reason for, you have various mixes, various water cement ratios, and that's the reason for the range. So the improvement to drying shrinkage, again, is based on the permeability of the concrete itself. So the more permeable the concrete is, then the better improvement that you're going to have to a point. I'm sure that there's concrete that is too permeable to respond well, but I haven't found it yet. So again, that's the reason for the range. Effects on permeability from the academic literature. Again, we call this, if something seems to, or is claimed to solve many, many problems, or is something that fixes all your problems, in the States we oftentimes call it snake oil. It's back in the old, that comes from the Wild West days, when they were settling out in Arizona and New Mexico. There would be these settlers that would go around selling these bottles of magic potions that would cure anything that was wrong with you. As a researcher, that's one of the first things that I thought when I first heard about this. I'm going, what? Snake oil salesman coming in here telling me it's going to do all this with concrete. But again, remember, it's filling the capillary voids. So it's reducing void structure, making the concrete more dense, and it has a lot of really good effects. So when we close those capillary voids with colloidal nanosilica, it closes off that route of ingress from water and other contaminants that can get into the concrete. Logically, it follows that maybe freeze-thaw durability is also improved. There are a lot of other things that research has shown. We're only focusing on compressive strength, shrinkage, and permeability today, but there are many others that we could talk about. And these are, again, a list of researchers. Not all of these. There are some that were spray applied, some were integral colloidal nanosilica, I mentioned. These photographs are some of the best demonstrations of the closing of capillary voids that I could find. And you can see, hopefully, you can see at least this number 4 here is pore space, and you can see how much it shrunk over here after a colloidal nanosilica treatment. Number 1, the area beside the number 1 here, so number 1 is CSH. The area beside the number 1 is a giant hole, and it's basically closed here. In this photograph here, you can see a giant pore space here, and it's gone. You can see the pore space here is not completely gone, but it is shrunk. This pore space is gone. So you can see that filling of capillary voids is something that you can see under scanning electron microscope, the filling capillary voids from colloidal nanosilica. Now, does it have an appearance that will jump right out at you and say, hey, that's caused from colloidal nanosilica? No, it doesn't, because the colloidal nanosilica's reaction product is the same as what normally happens in concrete. As concrete gets hard, the water and the cement react. Calcium silicate hydrate is formed. Well, the calcium silicate hydrate is the reaction product between the calcium hydroxide and the colloidal nanosilica. So when we look at it under a microscope, the key indicator is that the pore space is greatly reduced, rather than something jumping out and saying, hey, I'm caused by this colloidal nanosilica. So from laboratory testing, this is, again, University of Tennessee Chattanooga lab, as well as several others. The effects on permeability were mostly done by, in fact, all of these were a test method called AASHTO T259, which is the chloride ponding test. Some of these were run, depending on the mix, some of them were run for 90 days. Some of them were run for 120 days, and in one case, out to 365 days, to show the changes. And this is just chloride diffusion coefficient calculated using second order Fichtean diffusion equations. So you can see that there's quite a bit of improvement. Even some of them were tremendous improvements, and then some of them were less. It greatly depends on the concrete, the parent concrete. How permeable is that concrete? How reactive is that concrete? So my suggestion is that what the research has shown is it's going to improve permeability characteristics. It's going to improve compressive strength characteristics. It's going to decrease shrinkage. But to what degree it's going to do it to a certain minimum amount, but to what degree is dependent upon the raw materials. Like so many questions with concrete, when we talk about concrete technology, one of the first things I tell my students at the school is, just because a concrete mix design works in Chattanooga, Tennessee, doesn't mean that it's going to work in Atlanta, Georgia, or doesn't mean it's going to work in Dubai, UAE, because the raw materials are fundamentally different. And that's why folks like me have a job, is because there's so many variables that it's very difficult to track all those variables. And the best that we can do is to try to have predictive models that will tell us how the concrete is likely to behave. So when we have colloidal nanosilica being applied to concrete, my suggestion is to always, if there are general contractors, engineers in the room, my suggestion is to try it on concrete made with raw materials that are going to be used on the project, and do the testing to see what the effects will be with that particular raw material combination. This is just a continuation of the previous slide. You can see more improvements on permeability. Since this was done, I've since begun running some permeability testing using a new test standard called, or it's new to me, it's not that new, NT492, NordTest 492. Does anybody have any experience with NT492 in the room? All right, NT492 is a very fast electrostatic way to pull chlorides into the concrete. So you have calcium hydroxide on one side, sodium hydroxide on one side, sodium chloride, salt water on the other side. You induce a voltage, and then you can pull chlorides into the concrete and then measure the chlorides and how quickly. So it makes a comparison between untreated concrete and treated concrete with colloidal nanosilica. It makes it very fast and very easy to determine how well the concrete's going to improve. Here's a slide from a DIN 1048 test. So I did say that we did a lot of ponding tests on permeability, but we also ran some DIN 1048, which that's a European standard. This sample here, this was a particularly bad concrete with a water cement ratio of up around 0.60 or so. And this test here, let's see if I can figure out the pointer. This is a penny, US penny. This test here was stopped after only 20 minutes because the water was going through the concrete sample so quickly that they shut the test down. This was 72 hours, same concrete, the only difference being that this was treated with spray applied colloidal nanosilica. 72 hours, there was only about 5 millimeters penetration into the concrete. That's a pretty significant change in how that concrete was behaving. So this testing was done under hydrostatic pressure. The DIN 1048 test puts about, you can set it at different pressures, but I think we ran it at 7 bar. Just to give you an idea of how the concrete will behave under hydrostatic pressure. And you can see the improvements have been significant. And of course I did not do these tests here. This was done in previous laboratories. But you can see on up to here, DIN 1048. This is U.S. Army Corps of Engineers hydrostatic test. So all of these are DIN 1048 except for these. The only difference between the tests is that these are using pneumatic air to apply water pressure. So you have water and air pressure behind it. And this is using, the Army Corps of Engineers requires you to actually have a 100-foot column and drop the water into the concrete. So we're simulating, this is simulating the water column, and this is actually using the water column. So the average of all these tests is a 76% improvement in hydrostatic pressure resistance. Standard deviation of about 13%. So what does all this mean? If the colloidal nanosilica improves permeability of the concrete to this degree, how does it relate to how long the concrete's going to last? Some of you may have heard of Life 365, possibly in the room. Life 365 was a corrosion modeling software project several years ago It was undertaken by the American Concrete Institute, or ACI, Committee 365. They did it in combination with the American NIST, or National Institute of Standards and Technology, along with ASTM, the American Society of Testing Materials. And they put a lot of work into this to develop a conservative life expectancy model to try to get an indication of how long concrete would last, reinforced concrete would last, under chloride loading at various concentrations with various permeabilities. So the general idea behind it is that as permeability changes, permeability of the concrete changes, then chlorides will reach the rebar, or reinforcing steel, based on the diffusion coefficient at different times. So if the chlorides reach the reinforcing steel earlier, then the chloride corrosion begins earlier. The life cycle of the concrete is reduced with higher permeability. As the chloride diffusion coefficient is smaller, then it takes longer for those chlorides to reach the reinforcing steel, and the concrete will last longer. So we've begun using Life 365 to estimate gains in service life of concrete treated with a colloidal nanosilica. And we can see, it's kind of hard to see, and I apologize for that, but the next page will give you an idea. I'm going to go through just a few of the model ideas behind the model here. You set your rebar depth, your reinforcing steel depth, and the amount of cover, and then you have the depth of the entire concrete placement. This is done in a one dimension here. You can set it up in 2 dimensions or 3 dimensions. You set your surface concentration, but there are defaults in the system. So if you want to do a parking deck in New York City, then you can do a parking deck in New York City, and it makes some assumptions that de-icing salts are coming in on the car wheels and those kind of things. So there are some defaults in there that you can use if you choose, or you can set it up with your own constraints. Monthly temperatures are also fed into the model. And this is a probabilistic model. So what it means is that statistically, thousands and thousands and thousands of cases have been fed into this model to train it, to tell it when corrosion is going to most likely begin to occur. So I'd invite you to take a look at Life 365 and read the background on how they developed the model and how it performs and what it means. I'm not an expert on how it does it. I just have learned to use the model to help me estimate how long concrete will last. So we can see on this particular model, we used a 0.35 plain cement mix, plain Portland cement mix, no supplementary cementitious material. That was our base mix. I'll go ahead and change to the next page. So 100% cement, no supplementary cementitious material. The models predicted that the service life of that concrete was 20 years. 20-year concrete, I don't know too many engineers or owners that would be happy with concrete that was only expected to last 20 years. So the next thing that we did is we took a spray-applied colloidal nanosilica to this 100% cement concrete with no pozzolans, and we were able to extend the lifespan up to close to 30 years. So we gained 10 years, or a third roughly, by applying colloidal nanosilica. We used the chloride diffusion coefficients that I showed you earlier from the ponding test that we had run. So that we took an average from those, and we were able to reduce our permeability, and which extended the lifespan. So then we looked at 100% cement plus a spray-applied colloidal nanosilica and an integral admixture colloidal nanosilica. So we've been testing integral admixture colloidal nanosilica along with the spray-applied the whole time. And we can see that the two complement each other very, very nicely. So instead of having a 20-year lifespan, now we're up above 40 years. So we've doubled the lifespan, or even 2.5 times the expected lifespan, by reducing that diffusion coefficient of chlorides. We're keeping those chlorides away from the steel and making the concrete last longer. So the next case we looked at was a 25% fly ash mix. Fly ash, for those of you that may not be familiar with the term, fly ash is a byproduct of the coal burning industry for electric power generation. So I didn't really repeat that. I just, I wanted to do the spray only and then a combination of the two. Yes, sir?
About the integral CS, what's the percentage we talk about in the assumptions?
The percentage in here is, this was a liquid admixture, the integral was a liquid admixture done at about, I'm thinking in US units, about 1.2%. About 1.2% there. Now the spray applied is a little difficult to assign a percentage because you're spraying it and it depends on the porosity. So we did not, in a future study, I would like to weigh the samples before, weigh them after, and then I would have an idea of how much it absorbed. But for this study, I did not do that.
When you say it's applied in liquid form, I mean, is it liquid form slurry form, or is it liquid?
It's not. It's a very low viscosity spray.
Oh, right.
Yeah. So it's and it's very small particle sizes. So it's able to penetrate deeply into the concrete. And that's the other thing we'll get to in a moment is the actual application of the material. I'll get into that and explain that in a little more detail.
Any idea on the specific gravity of the liquid material?
The specific gravity of the material itself, it's about 1.1. So, all right, we'll continue. There'll be a time for other questions at the end. So if you'd like to put a bookmark there, then we'll continue on. So we had a case study in Port of Marseille, France. They had a test case that they wanted to try, a 70-meter long sporting quay, or sporting, I think my Australian friends will make fun of me how I say quay. We say quay in the US, I don't know what you guys say, but so it's a boat dock. and the Port Authority wanted to try spray applied CNS to reduce the permeability and attempt to reduce the number of contraction joints. They had seen the research and they saw that it could reduce shrinkage. So I recommended, from a stress analysis, I recommended that they reduce the number of joints from 7 to 3. But the Port Authority called me a couple of weeks after they placed it, and they said, Brent, we placed your concrete. And I said, okay, how did it go? And they said, well, it went great. We don't have any cracks. I said, well, how many joists did you cut? And he said, we didn't cut any. I said, you got to be kidding me. Yeah, then you got lucky. Okay. Spray applied colloidal nanosilica is not the golden prize for crack-free concrete, but it will greatly reduce the chances of drying shrinkage cracking occurring. You can move joints out further. How far, you might ask? Well, again, it's going to depend on the specifics for the project. It's going to depend on how permeable the concrete is, what the aggregate package is. There's so many variables, but it is something that we can that I can kind of have an idea of about how much, just from a mixed design analysis and an idea of how the substrate of the concrete is going to react with the concrete itself and those kind of things. So I did get lucky. It made me look like a hero to the Port Authority, but it was more luck than anything. I asked them to do 3 and they did 0. So the application of the spray applied, excuse me, please. The application is relatively easy. The particular product that we were working with was a 0 VOC product, so there was no danger to the environment or anything like that. And basically the way that they apply, and the greatest success that they've had, is to apply to rejection. So they spray the colloidal nanosilica and then they wait a few minutes and see if it disappears. And if it disappears, then it's being absorbed in the concrete. They apply again immediately. So it's only, there's a 15-minute window, excuse me, so they repeat 2-3 applications during this 15-minute window until it ponds on the surface after that 15-minute window. And then they know they have maximum penetration of the colloidal nanosilica into the concrete. And that seems to be when it works well. When I first heard about the product, one of the first tests that I did was I took a pan in my laboratory and I put some some of this colloidal nanosilica stuff in the bottom of the pan, this liquid. And I took an old concrete cylinder that I had sitting in the lab for a year or so, and I put it in there, in the pan, in the liquid. Went back to my office, did some work for Dr. Wino. My boss is here from UTC, making sure that I'm actually presenting here in Dubai, that I'm not off partying. So I'm doing some work, and I go back into the laboratory an hour or so later, and I see that the material has actually been wicked up into the concrete vertically. It pulled the product into the concrete vertically. That's when I told myself, hey, this is different. This is something that could be potentially an innovation. Let's see what we have here. And sure enough, it can actually be applied on vertical surfaces, walls, as well as ceilings. There's an ionic attraction that's going on there. It's the way it's been explained to me. I'm not a chemist, but it's chemically attracting the product into the capillary void system. I've actually seen with my own eyes it displace materials that are in the capillary voids. Did a project, it's not detailed here, I apologize, but we did a project where we took some salt, introduced sodium chloride into concrete on purpose, 5% by volume. We treated with colloidal nanosilica just to see what would happen. We were running half cell potentials on some rebar that I embedded in the beams. I came back the next day and I had a concrete beam that had white fuzz on it, about that thick, I don't know, 6, 7, 8 millimeters thick. You could write your name in it with your finger. And I called the guy that was sponsoring the research. I called him over. I said, you got to come look at this. And he came over and he said, well, Brent, what is it? And I said, it's salt. You know, we mix salt into this concrete, just purging salt out of it. He said, there's no way. I said, yeah, it is. He goes, well, how do you know? So I went, that's salt. So probably shouldn't have done that, but I've been around concrete my whole life, and I knew there wasn't anything that was really going to hurt me. So, but yeah, we've actually seen it displace things in the capillary void structure. It's preferred because of that ionic attraction. It gets pulled into those capillary voids. The reaction begins to happen, and it's making calcium silicate hydrate. And as it makes that calcium silicate hydrate, it's pushing anything else that's in that void system out. So I've seen on job sites that the company that was sponsoring the research, I've seen on job sites, they called me up. I've seen red wine purged from a pool deck. You know, I've seen some interesting things happen. So the penetration depth depends on the permeability of the concrete as well. We talked about so many things depending on the substrate permeability. But we've seen in the laboratory as well as cores taken from the field, typically somewhere between 50 and 300 millimeters is how deeply the product will go. It depends on the part. Cement ratio, again, permeability has so many variables. In some cases, shotcrete applications, we have seen as much as 250, 300 millimeters. So that's mostly a very permeable shotcrete applications at the higher level. But 50 to 150 is normal. We'll see 50 to 150 millimeter penetration on many of the samples. So, in conclusion, I think that we've shown that the academic literature is now understanding, the academic researchers out there are understanding that colloidal nanosilica may be something special, that it may be something that can help us with concrete durability. And our testing at the laboratory at UTC has confirmed a lot of that previous work, but also we've seen some things that some of the other researchers hadn't seen yet. But finally, the test cases, which include the Port of Marseille, as well as others now that have been done, has demonstrated that it's an easy product to apply, and that it's effective. When we saw 0 cracks on the Port of Marseille boat dock, we got lucky, but at the same time, if it hadn't been there, I'm confident there would have been some random cracking occurring. So that wraps up the presentation. 4 minutes at least. Yes.
On the application, you said that you would do 2 or 3 coatings until they get saturated, basically.
Yes.
What's the effect of temperature? Let's say you're in Dubai or a very hot area and your substrate is very hot. Are you going to waste product by doing it in the daytime? Or?
That's a good question. From what I understand, I haven't done, I haven't been involved in any case studies in any hot areas, but from what I understand from what some of the people have told me is that oftentimes they'll flood it with water first to cool the concrete and then apply the product, because the water doesn't keep the product out of the concrete.
So
The product
the water will evaporate and the product will stay inside.
Yes.
So it will be preferable to wet it up.
Yes. That's what I've been told. I haven't verified that in the laboratory, but that's what I've been told. Yes, sir.
This presentation about the colloidal nanosilicon, the very common one that is admixture used now is the microsilica itself. So did you carried out any comparison between the two for the performance? I just entered in the second slide, so maybe in the first slide you mentioned this. I don't know.
No, I didn't. But it has been significantly addressed in the academic literature where others have done that. And the idea is that the colloidal nanosilica is much finer than the microsilica or silica fume. The particle size is much, much finer and therefore more, just to sum up the academic literature, much more reactive than the silica fume itself. So the consensus is that it's much more reactive.
Sorry for the second question now. The other part is the percentage. The microsilica, the range is starting from almost 5 to 15. What's the common is that around 10% of the cementitious material is replaced with microsilica. In your case here, you are advocating 1.2 only percent of the mix. And this is totally different.
Yeah, for the
financially, you're also supposed to show some difference in the cost, and if this is true, then it will be much better compared to microsilica.
The integral admixture portion, was around that was 1.2%, and I didn't run any costs. Really, I just looked at it from an academic standpoint. So you may be right. I'm not sure. Yes, sir.
How long does it need protection after application?
No. From what I've seen is that when you say protection, the reaction happens very quickly, from what I can tell. I don't think you would want to immediately submerge, protect concrete and immediately submerge it with acid or something like that, immediately and expect to get too much. But 24 hours is probably a conservative time
Can I
period.
just,
Yes, of
you know,
course.
clarification of the question. I mean, when we say help immediately, it's like, okay, we use the silane saying before in here, the silanes and
Yes.
the silane on the surface. They are penetrative, right? And they do penetrate to a certain depth.
Right.
But what we find out, those silanes, because they are exposed to the weather and the atmospheric conditions, the silane effectiveness have gone. And this is, I think the question is, if I reword it my own way, is if I apply the material on the top of the concrete surface, am I protected now? Am I good for life? Am I good, or
Sure.
I have to reapply after 3 years
No.
or 6 years or whatever?
Now, what we've seen is because of the reaction products, it's not putting, the colloidal nanosilica is not introducing a foreign substance into the concrete. It is initially, but that substance reacts with the calcium hydroxide to form more calcium silicate hydrate. So
And it becomes an
that,
integral part of the
it's
process.
it's like filling the capillary voids with more concrete. It's not a foreign substance that has to be replaced.
Okay. One more thing, concrete in general, in the Gulf in general, and in the UAE in particular, is of very, very, very high quality. The gentleman there mentioned the microsilica, the fly ash, we've got dry blends, we've got, so we've got a very sophisticated concrete mix.
Yes, sir.
The strength, if we talk about the strength, is 60 Newton above. if you talk about surface absorption is less than 10 millimeter. If you talk about chloride iron probability is less than 1,000 coulombs. Okay, all that is a very dense concrete. However, in a lot of cases, like there's lots of basements around, there is a leak. There is a leak. And now, would it be the product, this product is a solution for me, first, because we talk about like crack sealing. Second is the chloride contamination and then the negating the chloride effect on the steel, the corrosion, the hot
Sure.
side potential there. Is it a solution for me, or is not going to work in a dense concrete like that?
No, we've run, there's been several tests done, a wide range of tests in the last 4 years, and some of that has been on concrete as a very dense concrete, as low as 0.35 water cement ratio with 50% pozzolans, and it's still effective. The effectiveness from a percentage change is going to be lower because it's not as permeable, but it is still effective, and the academic literature also shows that up to 50% supplementary cementitious materials and very low water cement ratios, that it still improves, and that's from the academic literature showing that it still improves the concrete quality. So it's something again that it's something that to determine effectiveness in the particular project or particular raw material combination would have to be just to play with, I guess, sort of. And that's something that I'd be willing to talk about as far as my experience and my background when using the material as much as you like. You can email me or call me, whatever you like. I'd be glad to talk to you. Yes, sir.
Talking about fair face concrete and architectural concrete,
Yes.
is it compatible with that?
It
Is it compatible with most common paints also?
It is, and the reason is that I don't know why, I can't explain it, but this particular material leaves the top 1 to 4 or 5 millimeters unreacted for the most part. So adhesives in the case of flooring, paints in the case of paints, colorants. There's been no issues with any of that I'm aware of. So because it somehow leaves that top surface unreacted. Any other questions? You guys have had some really good questions.
You did not mention any brands or producers, or is
No,
it very
I-
commonly available, or it's rare?
It is available. It is commercially available, but it's. I didn't want to mention a brand or producer because it's an academic study. Yes, sir.
Yeah, one more question. How long do you think it will take for attaining the full effect of this treatment?
The full effect.
Time duration.
Yeah. That's one of those famous concrete questions that the answer is going to be it depends. What we've seen is typically at 24 hours, we begin seeing significant compressive strength gains at 24 hours. At 7 days after applying, then we see some more significant gains. So I think you're going to see that it's an early process. So I will say that it continues to improve and it continues the process. But if I had to guess, I would say in the 7 days to 14 days, then it's going to be 95% completed. Yes, sir.
I heard some research is going on for self-cleaning concrete. Is it the same nanotechnology using the same
Did
application?
you say self-cleaning?
Self-cleaning.
Self-cleaning
Self-cleaning concrete.
I'm not familiar with that. I have done some self-cleaning concrete research on my own for pervious concrete, but I'm not familiar with
For clothing is produced already in the US. Some sprays with nanotechnology
Okay.
for self-cleaning clothes.
Self-clean. Okay. I'd have
But
to.
for concrete, I heard that it's going on some research for it.
I know that there are some photocatalytic cements that can clean the air and can reduce staining and things like that, but I'm just not familiar with that. Sorry. Yes, sir.
Just on the application, on the graph you showed a huge increase on lifespan of the concrete.
Yes.
What will reduce the lifespan of the concrete? surely there must be limitations because yes, it's going to fill the capillary, but let's say there's acid attacks. Does it increase your concrete's, resilience to acid attacks?
Yes, we have done significant testing with acid resistance. I didn't have the photos loaded up on the computer, but that's something that I could show you later if you'd like. But we've done hydrochloric acid testing as well as sulfuric acid testing for sewer. We're in the middle of the sulfuric acid testing for sewers project. So that's a continuing project. We hope to have some results out to be able to share sometime around February or March. Yes, sir.
You mentioned something about when you bonded the element within the solution, and it was like an induced chloride in it. The chloride came out on the surface.
Yes.
Again, because my background where I come from is like treating leaks and chlorides contamination,
Yes.
modeling the structure. I mean, because the owner wants the building 100 years now, it's been reduced because there's a leak and chloride has been reduced. Now, the second question: if I use the product to the surface, am I going to get the leaching of salts to the surface, and paint is going to be blistering and
Well, if you to apply the product properly, the paint would have to be removed.
no, paint is removed
Okay.
and I've applied it.
Yes.
Am I going to see the chloride leaching to the surface and get that leaching?
Typically, what I've seen in the laboratory is that leaching occurs, or the expulsion of the contaminants occurs immediately within the first 24 hours, and then you wash it off, and it doesn't do it anymore most of the time.
Before putting subsequent finishes on the top.
Yeah, you would want to wait to make sure that the purging action, the purging that the colloidal nanosilica was doing was over with before putting another coating or paint or something on the surface. Anything? Are we out of time?
3 more minutes.
3 more minutes? We have time for one more question. Yes, sir?
Yeah, we use for debris slab or bridge membrane and bituminous. This type of concrete is better.
It's hard to say if it's better, but what I would say is that just from an opinion, it seems to be better just simply because the change is happening inside the concrete. So since the change is happening inside the concrete and in the capillary void space, instead of it being a coating, it's in the concrete. And coatings, in my experience as a consultant and as a researcher, coatings will fail. And coatings fail often. So whether it's from traffic loads or weather or whatever. So for me, the idea that the change can be made inside the concrete structure is the real important point to recognize with the product.
I would not recommend that. I've seen big companies, international companies coming claiming that they are crack-free and your basement you don't need waterproofing and ended up with big lanes here in Dubai and main floor projects for you.
It's considered as a part of like waterproofing system or just only capillaries being filled and being reacted. So when you have a walls or you have a basement, it's considered this is a waterproofing enough for the walls. This is the question in summary.
It's very dangerous.
To say that if you have walls, which is you have experience and he has experience, you have walls and it's been in the basement, and you applied this material after, either you put it as additive or you have spray, is considered this waterproof now, no need any further?
I would, from an academic research standpoint, I'd have to say that based on the hydrostatic pressure testing, that in an ideal situation, yes, but I think that it should be carefully considered on a project-by-project basis, because if there are cracks, then I'm not sure what crack bridging ability the material has. It may have some, but probably not wide cracks. So each crack probably would have to be treated individually, and then those sorts of things.
Is it approved for the consultant?
Sorry?
Is it approved for the consultant to use?
Approved for consultants to use? I believe I would have to redirect your question to someone that might know elsewhere. So if you email me, I'll work on getting you an answer for that.
So you say again?
The approvals, what he's referring to is for a specific product or specific applications for specific approval. This is not a product, this is just a direction, this is a scientific study which may guide the future for a few further products and other.
You are right, but they never approve approving specific brand names with TDS and so.
So I can't really comment on the brand names in most.
Probably coming back to that waterproofing question, I think much depends on the positive and the negative side of the waterproofing.
No, I mean,
If you are talking on the inner surface, the consideration is different from the waterborne
Gentlemen,
surface.
the waterproofing subject is a very critical and should not really go in here. The remaining variable at the time of casting concrete is so huge. The water cement ratio cannot control, even if the supplier controls it for you. The workmanship of the worker on the pump will change it for you. The steel configuration, again, as per the designer, it has a big influence on the width of the crack. So this is not something a material, a magic can do it. People burned their fingers and their toes and their heads in this issue before. It sounds a perfect product, you know, as a durability, to increase durability on structure. If you are looking to improve your durability on structure, this is the way, I think. I'm convinced, you convinced me today,
Yes, sir.
that there is a product that can improve durability. Whenever durability lacks for whatever reason, or you want to improve it at the time of construction.
The
But
durability does mean it will give you extended life.
lifetime of the structure, probably the water penetration or the absorption, water absorption, chloride ion penetration because of if you are on the seashore, or on JR here or somewhere else, yes, probably. Yeah, other than that, probably.
Well, let me say thank you one more time before they kick us out of the room. Thank you very much.
Check tomorrow because I want to see if we can't for the
Okay.
If you,
Yeah, no, we're talking. Yeah.
maybe we'll just
And I saw. I'd be assuming that people bring books.
No, thank you. Thank you. I'm so sorry.
Thank you for coming. This is the product we're talking about.
I'm gonna wander ahead. I'm gonna wander back. Okay.
Hi, this is the product we're talking about. Hi, this is the product we're talking about.
I'm sorry. Let me grab a bag.
just
Yeah, that's what
This is the product we're talking about.
All right, thank you.
Hi, this is the product we're talking about.
Yeah, I'm a lot of these.
Hey, this is the product we're talking about. Hi, this is the product we're talking about. CNN. Thank you.
Could you give us your cards?
No, I've done it. I already gave you the card. Before we started, I gave him the card.
Very good work. So you done it once.
No, I
Well, thank you very much.
do lots of forensic engineering على failures.
Yeah.
I do.
What's your turn?
Anyway, it's really
Fantastic.
Finally, this is the part that we're talking about. CNS.
Please feel free to email me if I can. Of course, I'll send it. It's possible my email is there.
I'll send you
I need to talk to you.
It's an excellent.